Hi everyone. In this video we are going to continue talking about nebulae and star formation. So here we're going to get to these last two goals. We'll look at how star formation begins. We will explain protostars, how protostars form, how they move across the HR diagram, and then how they become main sequence stars. So young stars are always accompanied by a very large dense cloud of ISM. That's because stars are formed in this very dense ISM cloud. So not all dense clouds of ISM are going to be forming stars. There has to be compression. So if there's a very dense cloud, it has to be large, it has to be quite dense of material, this ISM cloud. If it becomes compressed somehow, if it's compressed to high enough density and also temperature, star formation will begin. But that doesn't happen all the time. It actually is pretty tricky. So in order for star formation within the ISM cloud to begin, it has to overcome thermal energy, meaning moving molecules and moving atoms. It has to overcome magnetic fields. So the ISM can't move freely through magnetic fields. Also rotation. So as a cloud starts to contract or maybe begin to compress, rotation is going to increase. So it has to overcome the fact that rotation might be increasing, as well as turbulence. So turbulence being sort of wind in the ISM cloud, which can stop the gas from contracting. So in order to get a cloud of ISM to start star formation, we need that initial contraction. So one of the ways to trigger star formation is through shock waves. So if a shock wave travels through a cloud of interstellar material, it can cause that material to compress and condense, and then cause the ignition for star formation to begin. So compressing the gases within that ISM cloud, the shock wave can start the compression, and then once the compression begins, gravity can take over and continue until star formation begins in that compressed cloud. So for example, a supernova explosion, which we'll get to supernovas later, sort of any explosion in space can cause shock waves that move outward from that object. If the shock waves move through a cloud of ISM, it's going to start to compress that cloud. That compression can initiate star formation within the cloud of the ISM. So for example, here's a zoomed in picture of this sequence here of this nebulae. So this is, it was a previous supernova explosion, and the shock waves blew outwards towards this large area of ISM and triggered a lot of star formation by compressing this really dense region of ISM. Another way that star formation can be triggered is within galaxies. So within a galaxy that has a spiral pattern similar to ours. So our Milky Way galaxy looks something like this. It's a spiral pattern. It's rotating, and the spiral arms on the galaxy work sort of like shock waves that are traveling around and through the galaxy. So if there is a cloud of gas in the galaxy, and the shock wave moves through the the shock wave moves through the cloud of gas, or the cloud of gas moves through the shock wave, meaning through the spiral arm, it can cause compression of that cloud. So that's what this diagram is showing here. Here we have a cloud of gas, which is an area of ISM. As it moves through that spiral arm of the galaxy, it's going to cause compression. So as it comes out the other side, it will start star formation because you're compressing that ISM, all that material. So what's happening is the shock wave or the spiral arm of the galaxy is causing that contraction, causing that compression. So the cloud of gas will start to contract, and all the atoms and molecules will start to fall towards the center. Contraction. As they start to fall towards the center, gravity takes over, and they'll gain speed as they fall to the point where we call it free fall collapse. So all of the atoms and molecules within the gas are sort of free falling towards the center of this cloud. The atoms are colliding. There's a lot of energy being moved around as the atoms are colliding, as they are moving. The temperature of the gas is going to increase. And then once the temperature of all of those gases is hot enough, it's going to start producing its own shortwave radiation within the core of this soon-to-be star. So the shock wave causes contraction of the ISM cloud. The cloud's going to begin to contract. All the atoms will start to fall towards the center of the area. It will reach the point where it's free fall collapse, where all the atoms are moving quite quickly towards what would be the center of the cloud, or the center of the area of collapse. The atoms will be colliding. The temperature is increasing due to all the motion. And then when it's hot enough, it's actually able to produce its own radiation. So short wave radiation. But the radiation can't actually escape the core. The object, which is not a star yet, is going to continue contracting. So when we get to the point where this object has been compressed enough and it's hot enough that it is emitting its own radiation, but it's not hot enough to generate its own energy by nuclear fusion yet, it begins to shine. And this is what we call a protostar. It's not quite a star yet, it is a protostar. So it's shining, it is emitting radiation, but it's not generating its own energy yet. So the protostar will continue to grow inside of the cloud of ISM. So it has been created from some of the ISM material, but it's still within a very large cloud. So the cloud will absorb some of the protostar's radiation. So remember, the protostar is emitting radiation at short wavelengths. The cloud of ISM will absorb it and re-radiate it at long wavelengths. So we are actually able to see protostars within clouds of ISM if we're looking at infrared wavelengths, because we can see where the ISM is re-radiating these long wavelengths. So the long wavelengths being the infrared wavelengths. If we look in the infrared and see an area of intense long wave radiation, we know that there is a star forming in that region. So we can see within that cloud that there are stars forming within that area of the ISM. So at this point, the object would be in the upper or middle right side of the HR diagram. So if we start at the beginning, the protostar is nothing. It's invisible. It's in a cold, thick, dense cloud of gas. As the protostar begins to form, it gets warmer. It also starts to emit light, so it has a luminosity. And then our protostar, as it begins to contract, it's growing hotter and hotter, but it is still hidden inside of the ISM. It's only detectable in the infrared wavelengths, the protostar. So here, this is the Orion Nebula, so a large cloud of ISM in the infrared. So where we see these really bright areas of infrared radiation, we know that those are protostars within the ISM material of this nebula. So there are stars forming here. So protostars are pretty difficult to observe because they are not very bright and they're still within that cloud. And they're generally quite deep within the cloud. You're not really going to have a protostar forming on the edge of an ISM cloud because of how protostars have to start. Stars spend only about 1% of their life as a protostar, so it's not a very long part of their lifetime. The protostar, let's say, forms, and once it begins ionizing the nearby gases, meaning ionizing the gases of the surrounding ISM, it will start to clear its view and break out of the cloud. So once a star is able to emit enough energy to clear the gas around it, clear the ISM around it, is when it becomes visible. This doesn't mean that all protostars that are forming from the same shockwave, the same explosion, let's say, will be happening all at once. So even though one star comes into view, there might be other protostars still within the cloud, still forming. So if we look at the Orion Nebula as an example, this same one that I showed here, where we know there are protostars forming, the Orion Nebula has one O6 star. So remember, O is the brightest, so is the hottest. So there's one O6 star within the Orion Nebula that produces all of the light for the nebula. So this very, very, very hot bright star ionizes all of the gases around it. So the next brightest star after this one bright star is a B1. So this is not warm enough. It is not emitting enough energy to ionize any hydrogen. So the glow of the entire Orion Nebula, here, this is in infrared though, remember, is from this one star, the one really bright, really hot O6 star. So if that star was removed, the nebula's emission would stop completely. So it's controlled totally, completely by this one star because it is bright enough. So the formation of this Orion Nebula, this image here is also in the infrared. Of course, the arrows are not real. Those are added to show motion. We're able to study the formation of stars within the Orion Nebula using IR observations. So we're actually able to see that active star formation behind the nebula by looking at where we have the intense output of infrared energy. We're also able to see that gas is flowing away from the region of protostars. So that's why these arrows are here. We're actually able to look at the motion of the ISM. So how are these gases and particles moving within this nebula? And how are they moving relative to where we know there are protostars, where we know there's star formation. So another interesting thing that can happen, we talked about star formation can be caused by shock waves, and star formation can be caused by a spiral arm in a galaxy. Star formation can also be caused by star formation. So the formation of a star can actually be a ripple effect, and it can cause stars nearby to begin forming. So if we have some massive stars over here that were triggered into formation by compression, we know there needs to be compression from stars that were formed outside of the image, off to the left side of the screen. The formation and compression of this region can actually cause some of the ISM to move away from the star formation. If you remember here in the Orion Nebula, we saw that once the protostars started forming, once we have active star formation, the gas within the nebula is going to move away from the new star formation. So once these stars started forming, the rest of the ISM is going to move away from the star formation. So these stars are forming, the stars start to ionize gas, it's going to drive and move all of the rest of the ISM material away. which can actually push ISM material into a region that already had ISM material, causing compression on its own. So now this star formation, clearing its area and pushing away ISM, actually causes compression further down the line. So compression in other regions, this is going to cause even more star formation. So it can be sort of like a domino effect, where the formation of stars in one area of the cloud causes motion of the cloud itself, which will then cause compression in another region of the ISM cloud, causing even more star formation. So if we're thinking about our favorite graph, the HR diagram, when the protostar becomes visible, we know that that is when it has cleared most of the ISM cloud around it, cleared all that material. And the protostar will be in the upper right-hand corner or side of the HR diagram as a protostar. So when the protostar becomes detectable at visible wavelengths is when it crosses this pretend line called the birth line on our HR diagram. So these protostars here are not detectable in the visible wavelength. We cannot see them until they've gotten to the point to where they're across this birth line. So once the star crosses the birth line, remember these stars are not moving in space. We're just looking at their temperature and their luminosity, thinking of how their temperature and luminosity change as they age. So we have our protostar. It's going to start warming up. It gets a little bit dimmer. Once it crosses this birth line, we call it a young stellar object. And this is the point where we're now able to see it in the visible wavelength. So the young stellar object, now we can see it in the visible, and that object will continue moving on our diagram towards the main sequence. So the young stellar objects are the objects after the protostar has crossed the birth line before it reaches the main sequence. So these are going to be very young stars. They're rotating very quickly, very rapidly, and they generally have a very strong magnetic field. We also know from looking at the spectra of these young stars that they have a very active chromosphere. So remember the chromosphere when we talked about the sun, the level of the atmosphere around a star. And they also have a really strong source of shortwave radiation. So they're outputting a lot of X-ray radiation. So protostars are, most all protostars are surrounded by a disk of material. So as the star is forming, as it is in that cloud of ISM, the cloud will start rotating around the center of the mass, the center of where that star is going to be. It's going to rotate faster and faster and faster until it begins to flatten and becomes a disk. So the star that is forming in the center will be surrounded by this spinning disk of gases. So most protostars, almost all of them, have this spinning disk of material as the protostar is forming. So something really interesting is the disk around the protostar or the young star can actually emit really high energy jets out of the top and bottom of the disk. So there's a lot of energy inside this spinning disk. We have the star formation. It's compressing. It's increasing in temperature. And the material from that disk doesn't actually become part of the star. So what we can see is these jets, as we call them. They're actually moving and pushing the leftover ISM material around the star and around the disk. So we can see these sometimes incredibly long and very fast jets of energy out of the center of a protostar or a young star. They're pretty cool. So this is actual images, actual observations. Here we have an artist's conception, so a drawing or cartoon diagram of what's happening. We have the spinning disk material, and then we have the jet of energy out of both the top and the bottom of the disk. So nebula come in many different shapes, and the shape actually tells us a lot about what's going on. This is a dark nebula, and it's affected by radiation, but also wind of nearby stars. So we can see how the ISM, or the nebula, the cloud, is being affected by what's nearby based on the shape, because it will be moved around based on what's going on near it. So stars are not always stable, especially as they're forming. So stars have a couple of different components that need to balance each other out. So there's gravity pushing inwards from the outside of the star towards the center. There's the internal heat, which is starting at the core and pushing outwards. And there's also internal pressure, so starting at the core, pushing outwards. So in this diagram, the gravity is the green lines. Heat pushing out from the core is the red, in addition to pressure pushing out from the core in the blue. So deep inside the star, it must be able to support all the layers above. So essentially, the pressure of everything inside the star has to balance the pressure of gravity outside of the star and the weight of everything pushing down. So when these are all in balance, the star, we say, is stable. So the star will be stable when the gravity balances with the heat and the pressure pushing outward, and the star will not expand or contract. It'll stay as it is. It is stable. So where would we find the highest pressure in a star? The edge of the star, the middle of the star would be constant throughout. The highest internal pressure of a star, we would actually expect it to be all the way in the center of the star. So where the weight of the star itself is pushing down on itself at the largest, pressure increases with depth. So similar to the Earth, as pressure increases with depth. And in all stars, both temperature and density also increase as pressure increases. So all three increase with depth as you get towards the center of the star. So if we think about energy transport from a star, it's the same types of transport that we see here on Earth. So energy always moves from hot regions to cool regions, so from high energy to low energy. It's always trying to balance, so everything in the universe is always trying to balance itself out. So if the inside of the star, the core of the star, is the hottest region, energy is going to flow outwards from the hottest region, the highest energy, to the coolest region, the lower energy. So there's three different types of energy transport: convection, conduction, and radiation. So convection is like boiling water, where you have a liquid or a gas transferring heat through some kind of fluid. Conduction is where we have the transfer of heat through a solid, through direct contact. So that would be if you're using a metal pot over a fire, the pot was hot, the handle was hot, you burnt your hand. That's conduction. Radiation is the type of heat and energy transport from the fire itself. So if we're thinking about pressure and temperature within a star, if there's too much energy in the core of the star, and it's too much for the gravity of the star to balance, the star will start to expand. That means that then the temperature inside and the pressure inside will actually decrease as the star gets bigger, and the reactions that are happening in the core will slow itself down to the point where it reaches a stable spot. If there's not enough energy in the core, the star will contract. So the temperature inside and the density inside will increase, and the reactions will increase as the star contracts, to the point where then the gravity balances with the star inside. So a star makes really just enough energy to stop the contraction but not expand. So a star tries to find that perfect relationship between the temperature and the pressure to the point where the star will be stable. So a protostar, after it crosses that birth line, becomes a young stellar object before it reaches the main sequence. So protostars are formed from that inward collapse. And remember that the center of the protostar is going to increase in temperature, it's going to increase in density. And then once the temperature and the pressure are enough, that nuclear fusion begins, and it begins to produce its own energy. So hydrogen will combine into helium, and the star will start to emit its own photons of light. So that outward pressure of energy is going to eventually balance the inward pressure to the point where the star is going to stop collapsing. It will be stable. So once that star reaches a stable size, it has become a main sequence star. Main sequence stars are very stable. Not perfectly, because the star is always consuming energy, but for the most part, main sequence stars are very, very stable. So what happens inside the star is four hydrogen atoms are converting into one helium atom. This means there's less particles. So instead of having four, you have one. This happens over and over and over. So there's less particles, which means there's less pressure within the core. So the star will then slowly start to contract as it loses particles. As it loses these particles, it's going to start to contract because there's less pressure inside. That means the temperature is going to increase as it contracts, and the nuclear reactions will start to occur faster. So the energy will be flowing outward. The energy that would be flowing outward is going to start to increase as the reactions occur faster. The outer layers are then going to expand. The star becomes larger, it becomes brighter, but then because it becomes larger, the star becomes a little bit cooler again. So as the star grows in size, it will be more surface area, which means it will start to cool down again, I should say. So we know that the main sequence is this center region of this diagonal center region of our HR diagram. Most of the star's life is on the main sequence. Young main sequence stars will be at the lower edge. Here we have 0 age main sequence is labeled right here, where we have brand new young main sequence stars. And then as the star ages, the luminosity and the surface temp are going to change, and the star will move up and to the right. So as a main sequence star ages, it's going to continue moving up and to the right along this main sequence line until it has exhausted all of the hydrogen within its core. So as the main sequence star ages, it's going to continuously be converting 4 hydrogen atoms into 1 helium atom, which means it's going to contract. The temperature is going to increase. It's going to increase its outward flow of energy. It's going to become larger and more luminous. So here we have, as our main sequence star ages, it's going to be converting those 4 hydrogen into 1 helium, and it will be increasing in temperature as we follow the main sequence. It is increasing in temperature, and it is also getting brighter. It is increasing in luminosity until the point where the star has used up all of the hydrogen within its core, and all that's left is helium. So the lifetime of a main sequence star, how long is it going to take to travel along this main sequence line, depends on the mass of the star to begin with. So a larger star, a more massive star, is going to consume fuel a lot faster it's going to have a shorter lifetime because it's going to use up the fuel or the hydrogen in its core faster. Low mass stars aren't going to consume that fuel as fast. They're going to have longer lifetimes. So they can be billions of years on the main sequence. And there are many, many, many more low mass stars than there are high mass stars. So here is the lifetime of an average main sequence star, specifically our sun. So from birth through the main sequence, it's gradually warming, and then what happens after is what we're going to get into next week. So about now, our sun's a little more than 4.5 billion years old, so it is within its main sequence part of its life. And then here I have some very cool pictures of different nebula that I wanted to show you because they're fascinating. So here is a dark nebula. This one's called the Pillars of Creation. This is the Helix Nebula because it kind of looks like a helix. It's within Aquarius, the constellation of Aquarius. This is called the Crab Nebula. This one is one of my favorites. It's called the Red Square Nebula. This is the Cat's Eye Nebula, for any of you that have cats. This one looks like a cat's eye. And here we have the Carnea Nebula. And these pillars are showing new star formation. So we can actually see the motion of this nebula caused by the formation of new stars. So here we have a little map of star evolution. So far, we have talked about how nebula become main sequence stars, and then next week we're going to go over what happens from there. How do main sequence stars then age? Why do they age differently? And why do they then end up as white dwarfs, neutron stars, or black holes?